Okay, so gravitational potential energy, okay, is not like kinetic energy, but is very similar. Okay, so kinetic energy, if something has kinetic energy, it has energy based on the fact that it is in motion. Okay, so if I throw a cricket ball at you, Dominic, then that ball, based solely on the fact that it has motion, has some form of energy. Because if it hits you, it's going to hurt. Okay, potential energy is basically energy that a body possesses because of its position. Okay, so another easy example is if I hold a ball up over my head, does that ball have any kinetic energy? No, it's not moving. Okay? But it has potential to do energy, because if I let the ball go, as soon as I let it go, it will become, well, it will get motion, right? And the amount of energy that it possesses is basically exactly the same as how high it is from, well, whatever object we're measuring it from. Okay? So when we think about potential energy, it's not something that has energy just yet. It has the energy stored, and based on whatever is going to happen next, it could have a certain amount of energy. Okay. Now we're not going to look at all kinds of potential energy because there are many kinds. I don't know if you guys, you also only just look at gravitational potential energy. Okay, but there are many types. So if you take a piece of elastic band and you stretch an elastic band, it doesn't have any energy yet because it's not in motion. But you know, as soon as you let it go, it has some form of energy stored. The same as a spring. If you compress a spring, right, once the spring is compressed, there's no kinetic energy because it's not moving. But if you could release that energy, right, something would happen. It would create motion, most likely. Okay? Now, to make life easier, we're just going to look at gravitational potential energy, and that's kind of easy, right, because it is very logical. It's very simply the amount of energy that something has based on gravity. Okay, because we all know gravity pulls. Oh, I'll cut this out in the YouTube video so you don't have to go through all the stress. You guys can see all right on the screen. Okay, so very simply, if we hold something up, or if something is like, for instance, a car that's on a hill, all right? Say I put the brakes on the car, that car has potential energy, right? Even if the hill is at a slope, right? There's still a weight component pulling the car down the hill. Now, the moment I say it's a smooth surface, in other words, there's no friction, say I release the brakes, that car will use its potential energy to roll down the hill. Okay, so potential energy takes many forms, not just a ball, not just in the vertical direction. Potential energy can happen on slope, but when we measure it in the vertical dimension, right? So up, down. Okay? So just like kinetic energy, if we want to calculate potential energy, if we take the mass of a car and we take its height, the potential energy is given by its mass times the gravitational constant times the height that it is. All right, now that height is how much distance I specify. Okay, so if I hold a ball 2 meters in the air and I say calculate its potential energy from the ground, what would the height be? 2 meters. But say I wanted you to give me the potential energy of the ball 1 meter above the ground. It would be 1, okay? So the height is what is given to you, right? So it could be anything, right? Obviously, it can't be 3 meters, right? Because that would imply that the ball could now drill its way 1 meter into the ground, okay? So there's a limit to that. But when you're calculating the height, it's a specific height that we are looking at, okay? And obviously, the higher the ball goes, logically, if we lived in a frictionless world, the ball would continue to gain potential energy. But now in reality, is that true? No. What's going to stop the ball from gaining potential energy? Yeah, it's going to, obviously, the higher it goes and the longer it falls, it's going to start losing energy transfer to friction. But obviously, in mathematics, we live in a perfect world, so I guess we don't have to worry about things like that. Okay? For now. Now, just to show you, right, what did I tell you yesterday about energy? What do we measure energy? What's the unit? The joule. Okay, so where's the joule here in potential energy? Okay, so the first thing I want you to look at is these two guys here. Mass times gravity. We've seen that before. What is mass times gravity? I want you to go back right to when we learned about forces. What is mass times gravity? What force can you think of that is mass times gravity? mg. Almost. It's the opposite of the contact force if you're standing on a flat surface. Your weight.
Isn't it weight?
Yes, weight. Mass times gravity is just weight. Okay? And what is weight? Weight's a force. And what's the unit of force? The joule. Sorry, not the joule, Newton. Okay? So weight is measured in Newton. So that mass times gravity, that's just the weight force of an object, which we measure in newtons. All right, let's think about the height of this thing. What is height? If we're talking in motion, what do we call height? Distance, or we have a special fancy way of calling distance now, if it's a vector quantity. Displacement, okay? And what do we measure displacement in? Meters. And what have we learned about something that is Newton meters? It's just isn't it just a joule? Newton meters are just joules. What was momentum again? Momentum was Newton seconds. And what did we simplify Newton seconds as? Yeah, okay. So they all sort of tie in together. So that's where potential energy gets its Newton meter or White's joules, right? So even though it's mass times gravity times height, how can it be the same? Well, if you simplify the units and if you break them down and you think, well, mass times gravity is a force and force times distance, right? Remember when we learned about work done, we said work done is force times some distance, didn't we? So force is newtons and distance is meters. And that's how all of these tie in together. And again, that makes sense because remember, in order for something to have energy, work needs to be done for that to happen, right? So if the ball is on the table, it has no potential energy. If we want to give it potential energy, we have to do something to the ball. We have to physically lift it above the ground. Some work needs to be done to lift the ball up. Okay? And because of the work done, we now have a direct relation between the work done and the amount of potential energy. So if you want an increase in potential energy, you need to do more work against gravity. Okay? If you want less potential energy, then work gets done with gravity. Right? Is it easier to pick a ball up or let the ball go down? Let it go down. Why? Because it's actually work with gravity. Whereas when you pick a ball up, it's work against gravity. Okay? And so that is the time between work and energy. Okay, so let's just go and look at some very simple examples to start off with. So it's the first one there says find the increase in potential energy in raising a sack 1 kilogram through a height of 3 meters. So the key thing here is increase in potential energy. Okay. So which way is the ball going? If it's an increase in potential energy, it must be going up. Because if you bring something closer to the ground, it has less potential energy. Does that make sense? Right? Because it's lower to the ground. Right? It's going to fall for less long. Okay, so an increase just means the ball's going up. In other words, our height has increased by, what did they tell us? 3 meters. Okay? So if we want to calculate the potential energy, we take the mass of the object, which is 1 kilogram. Oh, actually, before we go into this, I just want to go back to here. In your textbook, they've told you that you can calculate potential energy as 10 mg. Right? For y'all physics guys, I'm going to caution you to stay away from that because you don't want to get, you use a different gravitational constant. So I would say this is the equation that you should remember for potential energy. For you, Troy, that's easy because you know G is always going to be 10. We use 10 in mechanics, in mathematics, but they use 9.81, okay, as their constant for the gravitation. Remember, it actually changes depending on where you are. Okay, so even 9.81 is not accurate. It's an average. Okay? All right, so anyways, carrying on. We have the mass of 1 kilogram. We have the gravitational constant in mechanics of 10. And our height is, well, what was the height? 3 meters. Right, that's going to give us, it's a very difficult one. 1 times 10 times 3 is 30. And what's the unit of energy? The joule. Okay, the joule. Newton meters or the joule.